So, so if you've been here for the workshop this week, you will already have seen the definition of a category with duality. But let me just give it again. So, a category with duality is a triple C d eta, where C is a category, D is a functor from C up to C. So Marco called this star, but I don't like my functors to have such a name, so I call it D instead. And eta is a natural transformation like this. And then there's a condition, and the condition is that the quadruple D up D eta up eta is an adjunction. From C to C up. So in other words, a category with duality is a category and an adjunction from it to its opposite category, such that the adjunction is equal to its opposite. Sometimes we want to assume that this is an isomorphism, so then this adjunction is an adjoint equivalence. Let's let A be a ring, and let's C be the category of finitely generated projective right A modules. So if d eta is a duality structure on this category, such that D is additive, then what kind of data does that give us? Well, we can evaluate D we can evaluate D on the free module of rank 1. Then this is now an object in this category, and therefore it has a right A module structure. But A also has a left A module structure, and since D is contravariant, that gives another right A module structure. So this is a right A tensor A module by saying that y times A1 tensor A2 is D of the map induced by left multiplication by A1 of y times A2. And since D is linear, this is the same as that, which says that these two structures commute with each other. Okay, and then we let's see, and then we have another map. So we can go from here to alinear morphisms. So this sends y to the map that sends A to y times A in the second structure. That's an isomorphism. Then here we can apply duality. This takes us to here. I can put an up here if I want. Well, yeah, dA, and then we use this unit of the adjunction to get back to here. Oops. So all in all, this produces a map here, and this interchanges the two right A module structures. And this is a map of right A tensor A modules from L to itself that switches the two structures. And alpha is the identity. Okay. So note that there's no involution on the ring. If you read in the literature, there's always this anti-involution. And that's just a mistake. The reason that is there is because you made the wrong definition. You said that L is a bimodule, and therefore to undo that mistake, you have to have this anti-involution. But the anti-involutions have nothing to do with it. This is actually, if you read in Morita's paper about Morita equivalence, this is exactly what he does. Yeah. Let me give an example. Well, maybe I should say how you... No. Let me give an example to show you how this structure is that you have this structure naturally. So let K be a commutative ring, G a group. Then the group algebra is a co-commutative Hopf algebra. So if lambda is an invertible K module, then we define L to be lambda tensor over A. So here we use the co-unit of the Hopf algebra structure to view this K module as an A module, and then we use the co-multiplication to extend scalars up to A tensor A. And alpha is the identity tensor, the map that flips the two structures. So this is how you get the natural duality structure on a group algebra. You can identify, if this was K itself, you could identify this with one copy of A, but you have to choose which one you use. Do you use this or do you use that? And this avoids making that choice. Okay, so now if we have such a category with duality is exact if the category is exact and if the duality functor is exact. No. Well, there's one thing I didn't say, which is that this alpha gives you a map in general from A to hom A in where you use one structure. So there's a unique map of AA bimodules like this, and if you want the duality to be through isomorphisms, so that eta becomes an isomorphism, then you need this to be an isomorphism. And I did that in this example by having this invertible guy. And I don't think this is this being invertible does not imply this for a general Hopf algebra. Okay, so now let's define K-theory. So so define so define S2, 1. So we just do what we did before, except, or what Waldhausen did, and except that we replace 1 by 2 everywhere. So define this to be the full subcategory of functors here, such that for every mu from 2 to n, let's see, A of mu composed is not is the chosen zero object, and so is A of mu composed is 1. And the second requirement and 2 for every sigma from 3 to n, the sequence here is 4-term exact. So let me just say what this means. This means that this is an admissible monomorphism. This is an admissible epimorphism. So this middle map here will induce a map from a choice of co-kernel of that to here, and that map should be a kernel of the last one. Yeah. Okay. So, So now define a symmetric spectrum in real pointed spaces. So by this I just mean a pointed space together with equipped with involution with respect to the sphere S21, which is the one compactification of the complex numbers with the conjugation by K R of C R is the realization of S2R like this. If the involution is, if the duality is not strict, so if eta squared is if eta is not the identity, then this geometric realization here is a bit more complicated, but let's not get into that. And again, as before, if you have these diagrams, now these are bigger diagrams, if you have a sequence of such diagrams, you say that it's exact if it's pointwise exact, a weak equivalence if it's pointwise, a weak equivalence. And the duality here is given by using the duality in C. But then also the duality here, which reverses both of these. Yeah. Okay, and then as before, there are symmetric spectrum structure maps like this. So this is a spectrum with respect to a two-sphere, but that doesn't matter. What matters is that when we take fixed points, so the fixed points in this sphere, so G is this. This is the one-point compactification of the real number, so it's a one-sphere. We could also have defined such an equivariant spectrum using Waldhausen's construction, but then that would be a symmetric spectrum with respect to the sphere S11, which is the one-point compactification of the sign representation of G on the real numbers. And if you do that, then the fixed set is S0. So you don't get a spectrum on the fixed sets. Yeah. I'm not going to. So as before, we can define the direct sum K-theory. So let's just do it. So K R plus C d eta in degree R is this. Here. So where S21 is now the quotient of the two simplex by its boundary, and S2RR is just the R-folds mass product of this with itself. So the definition is completely parallel. That's what real means. In that case, yeah. So in the case where the duality is strict, then this simplicial set here will have a structure. It will be a real simplicial set. So should I explain what that means? So it means that you have some set here, and now you have an involution on that. And if we have a map like this, then this commutes. If you put that there and this one here, where theta bar of I is m minus theta of n minus I. And when you and then the geometric realization of this will have a C2 action. For the same reason that the geometric realization of a cyclic set has a circle action. Yeah? Yeah, the one, this one. Yeah. Yeah. Okay. So now, as before, we have if I say what? Yeah. Yeah, I think it just means you can talk about symmetric spectra in any symmetric monoidal category. That's what it is. Okay, and so yeah. So again, this is restriction along a function now here. Defined just as before. Okay, and yeah. So let me write up two theorems about this map. So if this is an exact category with duality, such that C is split exact, and the weak equivalences are the isomorphisms then this map from direct sum K-theory to Walthausen type K-theory is a weak equivalence. Note that there's no assumption here that 2 is invertible. The proof of this is you can find on my homepage. So Ib Madsen and myself is writing a book about this, and a part of this book is now on my homepage, and that part contains a proof of this. So this is one important theorem, because it tells you this is something where you can better understand. So this is a group completion type construction, so you can understand the homology of this, for example, and the homology of its fixed set. So if you want to understand what K1 is on this side, this is how you do that. And then the other theorem is the additivity theorem. So for every exact category with duality, the map from KR of S11 plus C3 to KR of S11 C3 is a level weak equivalence. let me not write that, let me just like this. Again, here, this category is equivalent to the category of stalks. So this is equivalent to KR of CD eta is 1, 1, 3. What does this set look like? It looks like I mean S11. So what does this look like? It looks like so S113 has let's see 0, 0, 0, 1, 0, 0, 1, 1, and 0, 1, 1, 1, and infinity. So it has these three. But note that this is precisely a free cell and a fixed cell. And when you have this theorem, when you know that KR breaks up diagrams of this kind, you can use that to break up any diagram you want. This is Marcus Lichting realized that this is the correct additivity theorem for when you have duality. Of course, it's equivariant. It does. Okay. Since the proof of that theorem is not in the book yet, let me give it here so that it will be preserved for posterity. Okay, so we modify McCarthy's proof, which I gave in the last hour. So let's see. Should try it. So let's see. Now here we have S21 of S11C 3 M, and then we have three maps to S21CM, S21CM, S21CM. Let's just understand this. So what is an object in S113? It looks like this. And the way the duality works is that you take the dual of this diagram, then all the arrows go in the wrong direction, and then you flip it along this line here. And what this map does is it picks out these three components. So let's say that this is the first, the second, and the third. So the way the duality is on this is that this guy has its duality, but these two, we use the duality on each of them, and then we also flip them. Okay. So now what we do is that here we make this one larger, S21CM. Oops. The middle guy we don't touch, and the last guy we also make larger, but on the other side. Like this. And so let's see, so here we have I1 upper star cross the identity cross I2 upper star, P1 upper star cross identity cross P2 upper star. And then going up here, we now get rid of the M. This is an M. And this is I2 upper star cross. This P. Like that. And then here we have like before. Okay, so now we want to show that this is an equivariant equivalence. And so the way we do that is that, let me put it. I think we can remember the theorem, so I'm going to erase that. So before we used delta 1, but now delta 1 will have an action. So that's, yeah. So it will not, so the fixed set of that will only be a point. So we cannot use that to make equivariant homotopies. We need something larger. And so what we do is we take 2 copies of S1. So define delta box blank to be delta 1 blank cross delta 1 blank, where we give each of these the duality structure from before, but then we also flip the 2. So what does the geometric realization of this look like? It looks like this. So here we have 0, 1, 1, 1, 0, 1. This was 1, 0. And 0, 0. And yeah, and this is the simplicial structure. But the way the duality works is that it's reflects in this line. So this line here is fixed, and we flip around that line. That's the action on the realization. So we can use this line here to make equivariant homotopies. So now let me say what the standard homotopy is from. From here to itself. So I will just give one of them. And here again, we have this duality structure here. So this is given by that h of x, y, and now here we will have 2 morphisms from m to 1, and then we define this to be phi 1 upper star of x and psi 2 upper star of y. So then this will give an equivariant homotopy. If we look at these, what the corresponding maps are here we have the identity, comma, P2 upper star, I2 upper star. Maybe I should write cross. The identity cross that. Here we have the opposite, P1 upper star, I1 upper star, cross identity. Here we have identity, cross identity. And here we have P1 upper star cross I1 upper star cross circle P2 circle. Yeah, so you can see that we get a homotopy between the identity and this map. So this proves that this is a equivariant homotopy equivalence, and you do the same thing higher up. Yeah. I should also say how you get this last homotopy using the Q and between Q circle J and the identity. So as before, we will have some given phi, we will have some map here. And then we take push-outs along everything with respect to this guy. But we will also have a map in here. And then we take pullback of everything along this guy. So we have to do both. Is that going to... Is the duality going to preserve that on the nose? No, it's not. It's going to preserve it up to unique isomorphism. And but that's what morphisms are in the category of categories with duality. So you still get a homotopy equivalence here. So everything here becomes homotopy equivalences of pointed spaces after realization, pointed real spaces after realization, and therefore this becomes a weak equivalence. Okay, so that's the proof. This has some nice consequences. So let me give some of those. So this proves that the real symmetric spectrum Kr is positively fibrant. So let me prove that. So let's see. So we want to know that if we go from here, I'm just doing it for the first one, and then to here, so we would like to know that this is a weak equivalence of real pointed spaces. So let's see, what do we do now? First, here I'm going to flip these two. Actually, let me say instead what we know. We know that if we put plus here, then this is a weak equivalence by Shimakawa. See here, this would not be true if we had, or you have to be careful if you have S11 here, because you need to have a trivial line in your representation to know this thing. Okay, and so now let's flip the two. Like this, and now the additivity theorem tells us that we can take that plus away. So this is the additivity theorem. This is, yeah, and then if we want a commutative diagram, we have to flip back. Maybe let me write this arrow in the opposite directions. And now here's the map we wanted to know is a weak equivalence. And yeah, so this way additivity proves the looping. So I'm going to take 3 minutes more and prove a theorem that Marco was quoting in his first lecture. Which is that the fixed sets of these KR, of this KR spectrum, is equivalent to his GW. So let's see. So if yeah, let's try to see if this is an exact category with duality, then this space or this real space, so defined the same way. So this is Marco's GW. If you don't know how to see this, ask somebody else. Oh, that's the fixed points. Yeah. So this and this are weak equivalent, are canonically weakly equivalent real pointed spaces. In particular, their fixed points are equivalent. Okay. So the proof of this is very similar to this proof. So let's see. So we begin here, and now we can go to here. No. Here. Again, Shimakawa tells us that this is an equivalence provided that pi naught of this is a group and pi naught of the fixed set is a group. It turns out that pi naught of the fixed set is a group, and for me that's a miracle. I don't understand why it's true, but it is. So this is a weak equivalence by Shimakawa. Yeah. Now we flip the two. Let's do that here. And the only thing I used to prove the additivity theorem were these two properties that S2 1 takes 0 to 0 and extends to a 2 functor. But S1 1 satisfies that too. So here we also have additivity, that this is that we can take the plus away. Here. Yeah. So this is additivity. Okay, so now we turn this around. And then we use additivity again to put a plus on this guy. And now I should have planned the lecture better, because I'm missing a line now. So let's put it here, because now we have to, now we flip these again. Oh, maybe it's not so bad. Let me put it here. No. 1 1 plus 2 1. Sorry. Like that. And then we can come to here from here. Why is this an equivalence? This is a theorem of Christian Moy, who analyzed what this S1 1 plus construction does on the level of homology. And well, so now we have it, the equivalence between these two. So so the fixed points in the KR spectrum is Marcos GW. Okay, sorry for going over time. Yeah. So let me say that. So there's a two category of categories with duality. And there's a two category of real spaces. Yeah, yeah. No. So a one morphism, between two here is a pair of a functor and a natural transformation from f composed with d to d composed with f up, such that a certain diagram commutes. And so but there is you can define a pseudo-functor from this two category of categories with duality to the two category of real pointed spaces, such that when you take the fixed set in that space, you get the geometric realization of the category of symmetric spaces. I'm a little so it's an equivalence. That means you have a functor in the opposite direction, right? But you also need, what about that guy? I didn't say this. I didn't say this is an isomorphism. It doesn't have to be an isomorphism. This need not be invertible. I'm not assuming that this is invertible. Why do I not? Because this is because in spaces two morphisms are automatically invertible. So you don't need that. No, but no, but I mean it's not so easy to make that pseudo-functor. It's yeah. But then I mean no. Maybe I'm not interested in that. I mean. I mean, this thing that you can turn a morphism around, this is very special. Yeah. Yeah.
What kind of property do you need? You need to extend this to one to a two-functor.
I just did.
Well, okay, so this is the construction. You need to know that it takes. I mean, you can have some real
No, I did it with S11. I mean, it's just horizontal composition of natural transformations. There's no problem.